Hello, and welcome to the presentation Integration Techniques in Geometry. My name is Lucina Sukesan. I'm a kernel developer in the discrete computation team here at Wolfram. So let's begin. Integrals, together with derivatives, are the fundamental, essential objects of calculus. Integration serves as a tool to solve problems in mathematics and physics involving the concepts that arise by combining infinitesimal data. Integration helps to find, for example, the area of an arbitrary shape. Here, the region is given by its implicit representation, and by integrating 1 over the region, we get its area, which is around 0.6. Another of the applications of integration is to find the area between two curves. All you need to do is to find the definite integral of the difference of the functions that define the curves. In our case, it is 88. You can also find the length of a curve. In this example, the curve is given by its parametric representation. Again, integrate 1 over the curve and you will get its length. You can calculate the volume of a solid. Here the solid is generated by revolving x squared around the line y equals 1. This integral here gives its volume, which is approximately 3.35. Wolfram language has the same integrate function for different types of integrals. Integrate fx gives the indefinite integral of function f. Just like that, the indefinite integral of cosine is of course sine. Integrate f x minimum x maximum gives the definite integral of function f from x minimum to x maximum. Integrate f x minimum x maximum y minimum y maximum and so on is the multiple integral, for example. And finally, this integrate is the integration of function f over the region reg. Here, we integrate x squared plus y over a unit disk. Integration over regions is going to be the main focus of today's talk. Wolfram language supports integration over standard geometry regions. For example, we can integrate over a one-dimensional region, in this case an interval, over a two-dimensional region, a triangle, over a three-dimensional region, a tetrahedron, for example, over an n-dimensional region, in this case a five-dimensional ellipsoid. Integrate also supports integration over formula regions like implicit and parametric regions. Mathematically speaking, there is no such a thing as integration over regions. There are different kinds of integrals that are extensions of proper Riemann integrals. They are line integrals. Line integral is an integral where the function to be integrated is evaluated along a curve. Line integral is for one-dimensional regions. For instance, a curve can be a circle or a line, and these are, in fact, line integrals. Next are surface integrals. Surface integral is an integral where the function to be integrated is evaluated on a surface, for example, on a sphere. Multiple integral is an integral where the function to be integrated is evaluated on two-dimensional regions like rectangle, triangle, polygon, and so on. These are double integrals, and this is an example of a double integral. Three-dimensional solids like cone, tetrahedron, bowl, these are called triple integrals, and this is an example of a triple integral. And finally, n-dimensional regions like n-dimensional bowl, simplex cuboid. These are called multiple integrals. Here we have a five-dimensional bowl, and we integrate this function over it. There are also improper integrals in mathematics. Improper integrals are integrals where the function is integrated on an unbounded domain, like half-line, infinite line, and so on, like in this example, which is also a line integral. And so all these different types of integrals we call by a general name integrals over region. One of the most common techniques we use is the integration by substitution. If this technique fails, then we have to think and apply other techniques. Integration by substitution allows us to turn region integrals, rigorously speaking, line, surface, or multiple integrals, into a multiple definite integral. For example, it turns this integral, which is an integral over a disk, into this one. And as you can see, they are equivalent. In 2 words, the mathematics behind it. Suppose we want to integrate function f over a region reg. Suppose the region reg has the following parametric representation. We substitute variables x by their parametric representations, and we get a new function f whose variables are now u1, u2, um. And so, the original integral over region reg is now equivalent to this integral. As you can see, a certain coefficient k appeared in front of the function. What is it? Well, the value of k is different for different types of integrals. It equals to the absolute value of the determinant of a Jacobian matrix of substitution when we have a multiple integral. It equals to the square root when we have a line integral. And it equals to the vector product of the partial derivatives of ji's when we have a surface integral. Let's apply this technique to the previous example. In this case, f is x squared plus y, and the region is a unit disk. To get the parametric representation of the region, we can use region convert in the Wolfram language. And now we substitute variables x and y by their parametric representations, and we get a new function func. Since the integral is a multiple integral, we need to find the Jacobian matrix of substitution. We can use resource function Jacobian matrix. This is the matrix, and here we get the determinant of that matrix. So the coefficient k is the absolute value of minus t, and our integral is in fact equivalent to this definite integral. Okay, so suppose the function f is a certain type of a function, not just a general function we don't know anything about. Depending on what kind of function it is, there can be different techniques applied. For example, suppose that f is a polynomial function. This is the easiest case to deal with. Here, depending on region, there are, in most cases, closed-form formulas for the integrals. Let's say the function f is this polynomial function, and the region is a unit ball. Well, in this case, we have a closed-form formula. Coefficient rules just gives the list of exponent vectors and coefficients for all the monomials in this polynomial. And that's all we need. And this is basically the formula that is applied to the function, which is described, in fact, by CR. We just add the corresponding integration values over monomials, and we get the result. Of course, one would always like to apply a formula rather than use a substitution technique. One of the reasons is how fast, almost instantaneous it is, as it just replaces variables in the formula and calculates it. In many cases, no elementary formula exists for a given integral, and the standard techniques like integration by substitution do not produce a result. When none of the techniques is useful, we have to individually approach the integral, and sometimes very nice formulas exist for the integral. So some time ago, we were stumbled upon this integral. Yes, you could define the values of x, y, and z and numerically get an approximation, but this is not precise, and by just looking at the integral, one feels that there must be a neat formula. We at first tried to do math on a similar two-dimensional case of the original integral. Again, you can numerically get the approximation. So basically, we need to integrate this function over a unit disk with origin 0, 0, where x0, y0 is an arbitrary point. So we did some math, and it turned out that there's a very nice formula for this integral. Denote by d the distance between the point x0, y0 and the axis origin, and by k this value. And this is how the formula looks. It contains elliptic e and elliptic f functions. One exception though. Suppose the point is on the boundary of the region, that is, d equals 1, and consequently k is also 1. Elliptic e has no issues, but elliptic f function gives complex infinity. But it turns out that the least limit exists in this case. This is basically the formula when k and d tend to 1 and is equal to 4. And so when the point is on the boundary of the region, the value of the integral is 4. Once there's a formula for a unit disk, it is very easy to get one for an arbitrary disk. This is how the formula looks for an arbitrary disk, where AB is the center of the disk and R is its radius. Similarly, the exception is when the point is on the boundary of the region. That is when d equals r and k is 1 again. Again, if we apply limit, we get the result and the answer will be 4 times r. And so, when you evaluate this integral in Mathematica, this exact formula is used. First, it's precise. It gives you the exact answer, just like this. Let's compare it to an integrate. Secondly, it is much faster than the numerical approximation. Just look at the timings here. That's the integrate, and that's the n integrate. Let's now return to the original integral. It was a little easier to get the formula for this one than for the previous integral. So the goal is to integrate this function over a ball. Let's jump to an arbitrary ball now. So ABC is the center of the ball, R is the radius, and x0, y0, z0 is an arbitrary three-dimensional point. Again, denote by d the distance between the point and the axis origin, 0, 0, 0. And this is how the formula looks now. Very nice. And so the two exceptions here are when the point coincides with the center of the ball, and 2, when the point is on the boundary of the ball. Again, by applying limits, we still get very nice formulas. So that exact formula is used when evaluating this integral in Mathematica. Again, it's precise. It gives you the exact answer. And now let's compare it to an integrate. And it is much faster than the numerical approximations. First, the repeated timing of integrate, and now of an integrate. And with this, I would like to end my talk. Thank you for your interest and attention.
Well, once again, thank you for your attention, and I would like to say that if you have any questions concerning discrete computation, any questions about number theory, graphs and networks, geometry, you can visit our office hour, which is tomorrow at 3 p.m. on Friday. And also our virtual booth, this discrete computation virtual booth, is open every day from 8 a.m. to 5 p.m. You can also drop in and chat with us. Okay, so I see some questions. Can you share your notebook? Oh, the notebook is already shared. If you go to the list of the sessions and there's an abstract there, it says, there's a link that says download slides. The notebook is already there, so I shared them. You'll find it. Another thing is, what is the easiest way to find the surface area of a region on a sphere bounded by lines for Wolfram language? Well, I think you mean the spherical lines that are on the sphere. And I don't think there is an easy way, but maybe to first get the implicit representation of that region. Well, first, what is a spherical line? It is an intersection of a plane and a sphere. Maybe do a regional intersection to get that, and then see to get some representations for those lines, and then maybe do implicit representation, implicit region of those lines. The combination of those lines, I have to look at carefully, and then do something with that. Really, not an easy way. I don't think so. If that's what you meant. Well, yeah, elliptic case all those elliptic functions are related to each other. Well, we don't use an elliptic k here, but I believe we can. I believe that in the formula here we can replace the elliptic. I believe we can replace the elliptic e or elliptic f function with the elliptic k function with just one attribute. Writing the SQRT is the Laplace transform, then exchange the Laplace transform interval with x, y, z interval to the x, y, x interval to arbitrary dimension n. I believe so. Yes. The n-dimensional. Yeah, and we have to try that. These are not these are like mathematical questions, but I believe so. We have to try that. Yeah. And I believe this question is about the integrals that I'm talking in the last slides that are about the unique approach to those integrals. Okay, I see. Is there a geo-integrate for integrals over the Earth's surface? No, there's not a function like there's not geo-integrate function, but integrating over geo regions is something that we work on, and hopefully, yes, we will make it through. And the next versions will have those features as well. And I think if that's it, you can still leave your questions. I will answer them. Thank you for your listening. Thank you. Goodbye.